everyone, I'm Brandy, an OpenSciEd teacher and professional learning facilitator. Welcome to OpenSciEd Chemistry, Unit 1, Lesson 9. This is an important lesson where our students will focus on investigating density to determine why warm salty water sinks and causes glaciers to melt. Let's take a look at how we got here. So during lesson 8, we figured out indigenous knowledge is how people pass on what they know to their children over many years. We heard from Inuit hunters and fishers about how the sea and the ice conditions and the animals in the circumpolar region have changed over time. Both the berm solution and cutting carbon emissions could slow the transfer of energy at the interface between the warm ocean water and the glacial ice, but through different mechanisms on different timescales. In this lesson, we're wondering, why does the warm salty water sink to melt a glacier? Here's the lesson at a glance. This is a 3-day lesson where the students will be investigating the relationship between the mass and the volume of different types of water. You'll want to prepare the salt water and the freshwater containers 1 day ahead of time so that they can cool in the refrigerator. There are 4 related videos that are all teacher facing, so you'll want to check those out ahead of time too. There are 3 big parts in this lesson. Let's see what's happening in each. In the first loop, we plan and carry out an investigation where we're comparing the masses of different water samples for assigned volumes. Students add their data to the class spreadsheet. Then you create graphs of the class data with lines of best fit, which you will use to calculate density. We figure out that the density of a substance is its mass per unit volume, or the slope of the best fit line. You'll also have a chance to discuss significant figures here as well. And we wonder what we could do next to figure out if density differences we calculated actually explain why the warm salt water is on the bottom of the bay. In the second loop, we conduct a water density layering demonstration with different types of colored water to help the students see that the results can explain warm, salty water staying at the bottom of the bay. We figure out that when denser fluids are added above less denser fluids, the denser fluids sink. We also figure out that when denser fluids are moved beneath the less dense fluids, they tend to remain separated and flow independently of each other. So now that we know that warm salty water is melting the glacier, we wonder, how can we model the energy that is being transferred? In the third loop, we model the energy flow from the water to the glacier that causes melting. We figure out that changes in energy and matter happen together, including in convection, when the energy transfers as the substances move. Though we now see how creating a barrier at the bottom of the ocean would prevent the warmer salt water from coming into contact with the bottom of the Ilulissat Glacier. From the OMG data, we see that the temperature of the water is not that much higher above freezing, but is it significant enough to cause the melting? So we figured out that density of a substance is its mass per volume, that the less dense fluids are above and the denser fluids sink, and that changes in energy and matter happen together, including with convection. And now for the key moments. So in part 4, the students will conduct a density investigation where they're measuring the mass and volume of 4 different samples of water, warm and cold versions of fresh and salty water. This is a very straightforward investigation, but there's a couple of things that you'll want to plan for that I'll talk about more in the tips and tricks section. In the key moments for parts 5 through 7, now that we have the data, we'll use the Google Sheets to make sense of it. So begin with a teacher demonstration of how to make a line of best fit in the Google Sheets. Then in part 5, the students will compare the steepness of the slope of the lines, and we'll find the saltwater samples have steeper slopes than the freshwater ones. In part 7, introduce significant figures to help the students to determine the correct densities for the ice and microbeads. In parts 8 and 9, first with part 8, you will demonstrate the layering of the 4 different colored liquids that are listed here. Then in part 9, help the students make density connections to the Ilulissat Glacier and Disco Bay model, and help them to determine where each of the water types would be present in our model. Finally, in part 11, we'll discuss how the students would model the energy flow to the glacier that causes melting. Then you will begin to build the matter, energy, and forces, or MEF triangle. This is a critical first step to building a chart that you will use throughout the rest of this course. It's also used in the physics course, so the students will have a chance to apply the knowledge that you are building right now in the future. The key point for beginning the MEF triangle is that energy transfers and matter changes happen together. So, where do we go from here? We figure out that changes in energy and matter happen together, including in convection. And though we now see that creating a barrier at the bottom of the ocean would prevent the warmer salt water from coming into contact with the bottom of the Ilulissat Glacier. From the OMG data, we see that the temperature of the water is not that much higher above freezing, but is significant enough to cause melting. So in the next lesson, we'll use an investigation and simulations and mathematical modeling to examine the energy transfer when the substances are in direct contact. Okay, now for a few tips and tricks. So part 4, this is the mass and volume lab. You got to remember to prepare the salt and fresh water containers the night before so that you can refrigerate the samples. You'll need 2 in the fridge and then 2 on the counter, and you'll need a set for every class that you teach. This lab will definitely require more time than the 15 minutes that's listed in the teacher's edition. So if you have a block day option, you might want to plan to do it then. For materials, I had a central table where I put the 4 containers at the beginning of class, and I used colored paper that matched the colors on this Google spreadsheet that I made signs for that I laminated, and I put next to each type of water. You'll also need to provide a copy of this Google sheet for each of your classes. Students will need to add their data to the same class Google sheet. So I just share mine in a Google Classroom. From my experience, most of the students have little to no experience with Google Sheets. So in part 5, after the group has collected their data and added it to the Google Sheet, then they need to make a graph. And there's a video on graphing the Google Sheets that isn't in the slide deck, but it's located in the beginning of the teacher's edition in the preparation section. And I just choose to share that with all of my students so that anyone who needs to know how to can make it. Later in part 6, I also show my students a video on calculating density in Google Sheets, and then they help me perform that same calculation for our class data. In part 8, I actually don't do the water layering demo. Instead, I show the 2 videos that are in the materials preparation section at the beginning of the teacher's edition because I feel like my students can see the results much better when they're projected on my large screen than if I had like all 30 of my students crowded around a small glass in the front of my room. I also don't play the video straight through. I pause the video frequently after each water type is added, and I have my students draw a diagram like this one in their lab notebook. It's cool if you want to do this demonstration live. I just recommend that you try it by yourself first and make sure that you've added enough of the coloring to the different layers so that they're easily distinguishable. In part 11, as a preview for coming attractions, here's a sneak peek of where we're going with the MEF triangle. So in C2, we'll add forces, but don't add that yet. I decided to make a large poster that I could move around rather than trying to cram it all on the bottom of the rules and energy transfer anchor chart as suggested in the teacher's edition. So if you are going to do this, make sure you leave room for the forces part below matter and energy. In this lesson, we encounter meniscus as the students prepare to investigate the mass and volume relationship. And then there's a nice graphic to help jog the students' memory that's in the slide deck. After you're updating the particle model in part 9, you'll co-construct the definition for convection. For poster management, you want to have several anchor charts available from the previous units. The mathematical anchor chart from lesson 4, the rules for energy transfer models from lesson 2, and remember you'll just be starting the matter energy forces triangle, so I suggest a whole new poster rather than sticking it to the bottom of the rules for energy transfer. All right, that's it. So, to recap this lesson, the students investigated the relationship between mass and volume to figure out the density of the different types of water. Through this lesson, they now understand why the warm, salty water sinks to melt the glaciers through convection. Up next is lesson 10, where the students will learn about how we can measure the energy transfer a berm could prevent. Good luck and have fun.